So as we just mentioned, using tables is not always the best way to take derivatives of functions where you actually have the function and not the graph. The better way would be direct substitution, but direct substitution depends on the limit laws. So what we're basically going to do is go ahead and plug the number in so long as the value that we're plugging in exists in the function. It's in the domain, where remember the bulk of what we're looking at is the domain is whenever the denominator is not 0. You could also have issues with not being in the domain because the point doesn't exist at all, or you have a even root of a negative number, but for the most part, you're going to just kind of see what happens as you plug the number in. So what this is saying is if you're trying to find the limit of the f of x function as x gets close to a, direct substitution says go ahead and then just plug a into the function. So the limit as x approaches 5 of this term, I'm just going to plug 5 where the x is, clean up the math, and get 8 as an answer. 8 exists, so the limit exists and is 8. Now, I mentioned that we also have to focus on the limit laws, and basically, so long as the limit exists, we'll say of f and g as functions of x, where x is approaching a, then if you have the limit that is a sum of two functions, you can break it into two separate limits, the sum of two limits. The limit of the subtraction of functions could be the limit of one function subtract the limit of another function. If you have some sort of constant or multiplier times your function, you can actually kind of pull that out, then take the limit of your function. You've multiplied by a constant. The product of functions as a limit could be the limit of one function multiplied with the limit of another. Same thing goes with divide, but be careful. F divided by g may have a limit, but the limit of g by itself needs to also exist. It cannot be 0. And then I kind of group laws 6 through 11 as the exponents. If you have the function that is to a power and you're taking the limit, you could just take the limit of the function and then that result to whatever exponent or power you have. The limit of a constant is a constant. We'll talk about that in a second over here. But I wrote this into the exponents because if you think about it, you have x to the 0 power, which is really 1, so the constant is only there. Think about this for a minute. I have some function f of x that equals 2. That means I have a horizontal line at 2. It doesn't matter what number you plug in for a, you're going to always have a height of 2. Whatever that constant value is, regardless of what a is, that's going to be the height, the output for your limit. Obviously, if you have a single variable, then whenever you plug a in, you're just getting that single variable. But the limit of x to the n is you could just say, well, I'm going to take a, and that's to the n power. Radicals, remember, are fractional exponents. But even this law kind of has a second piece in the sense that you could think of the radical of the limit. Of course, if it's even, we have to worry about our negative, so we do need the function to be a positive limit. So here's an example for two cases. I'm asked to take the limit of some g function minus an f function as x goes to 5. Well, I'm told that I can, by the limit law, break it into the limit of just g as x goes to 5, subtract the limit of x as f goes to 5, and I was given that the limit of g as x goes to 5 is the same thing as 9, so I can just substitute 9 where I have this first limit piece. I can take the second limit and just substitute 8. 9 minus 8 is 1. There really should probably be brackets here. But I have the limit of an f function divided by the square root of a g function. So I can take the limit of just the f function, which we previously said was 8, and using the limit law 11, not just the square root of g, but bring the limit on the inside, because we know the limit of g is 9, the square root of 9 is 3, and I've got the